This liquid metal is under vibration. The liquid's called galistan. It's an alloy of gallium, indium, and tin. When the vibrational frequency is tuned just right, something remarkable happens. The metal droplet begins oscillating in a star-like pattern. I've been calling these things galinstars. Let me show you how I made them, and then we'll talk about the physics that makes them possible. Galistan is a metal alloy that's a liquid at room temperature and honestly just fun to play with. I've used it in a lot of chemistry experiments before, and many of my viewers asked a simple question. What would happen if you sent sound waves through that stuff? That's a great question. So I got out my Chladni plate. It's that thing you sprinkle sand on, and then you send sound waves at different frequencies through it to see different patterns. So I taped a petri dish to the Chladni plate, dropped in some galistan, and then started sending sound waves through at different frequencies. At first, nothing happened. Then around 200 hertz, I noticed the droplet beginning to ripple. And at lower frequencies, the vibrations got even stronger. And then I noticed the sound was generating capillary waves in the metal. From previous experiments, I knew that these waves could cause star-like patterns in water placed on a hot surface. But unfortunately, a thin gallium oxide coating on the galistan surface made it stick to the petri dish. And this prevented the formation of the star-like oscillations. But it was chemistry to the rescue. A few drops of sodium hydroxide solution chemically removed these oxides, allowing the galistan to pop back into a liquid bead. Then it was back to the experiments. What you're seeing here is actual footage of the first time my students and I captured a galinstar.
18, 17, 16, 15, 14. Yeah. I love it. Beautiful. Yeah, it is.
Ultimately, we ended up with this setup, sticking the galistan in a spoon and using my high-speed camera to collect footage. And this is when things got really interesting. We learned the star shapes aren't random. They have natural vibration modes, just like guitar strings. And the modes we saw, they're described well by a classic result in fluid mechanics called the Rayleigh-Lamb equation. It basically says the frequency of the star with a certain number of lobes depends on the radius of the droplet, its surface tension, and its density. We tested this by measuring the oscillation frequency of each galinstar with the high-speed camera footage. Then we calculated the expected frequency by plugging in the number of lobes, droplet radius, galistan surface tension, and galistan density into the Rayleigh-Lamb equation. When we did this, we usually got good agreement between the measured and predicted frequencies. But the driving frequency from the Chladni plate was almost always twice the measured frequency.
I wonder if what's going on with the frequency doubling is like a swing, where you got to move your legs forward and back through one full swing cycle. Notice my legs change position 2 times per swing. And I got to do it at the right rhythm, at the right frequency, to get the swing to work. This is known as parametric forcing. And I think that's what's going on with the Chladni plate and the galinstars.
This relationship wasn't always perfect, like the case you see here. This galinstar seems to be oscillating between a square shape and a dog bone shape. And I also noticed the relationship didn't seem to work quite as good with galinstars that had larger number of lobes. I'm still working on this experiment and would love any insight or suggestions people might have about what's going on. But I tell you what, I'd love to do this experiment in microgravity. Anyway, a special thanks goes out to all my viewers who suggested I try putting sound vibrations through galistan. Be sure to let me know in the comments if you did this. Happy experimenting, everybody.